Good afternoon in the East, good morning in the West, and welcome to USC Annenberg Washington Forum, virtual today, on the first commercial industrial scale fusion-powered electric power plant. Looking ahead, our next USC Annenberg Washington Forum will be next Monday, July 28th at 9 a.m. Eastern Time, online and in person in Washington, D.C. It's our monthly Africa-US Forum with speakers from around Africa and here in Washington, D.C., discussing this month's meeting of the BRICS countries' leaders in Brazil and the outlook for BRICS adding Egypt, Ethiopia, or other African countries to the group. But now to today. This program is on the record and is being recorded. The video will be on our website shortly, and you can see it on our YouTube channel. We'll be getting that out to all of you. This forum is part of a series on disruptive technologies. We've been focusing mainly on artificial intelligence and digital media, so this is a new topic for us. Our guest today is Rick Needham, Chief Commercial Officer of Commonwealth Fusion, which is a spin-off of MIT Research. We'll hear more about that shortly. Rick is an alum of the Naval Academy, MIT, and Harvard, and we'll put his bio into chat. And now the news. If you missed the Wall Street Journal story a few weeks ago, nuclear fusion, quote, has never been used for commercial energy production. But Rick, your deal with Google, again quoting the Wall Street Journal, marks the first direct deal between a customer and a fusion energy company, and the largest deal of this scale in terms of energy provided. So this is big news. Rick Needham, the floor is yours.
Super. Thanks, Adam, for the introduction, and thank you to USC Annenberg about having this series and hosting these interesting topics. I'm excited to be here to talk about commercial fusion. To cut to the chase, the recent deal that we announced is a huge mover for commercial fusion, with a Google announced deal with Google where they would take half the power from our first power plant. It's also a broader partnership agreement where they've come in as an investor. They've already been an investor, but now they're coming in with even a greater amount of investment. But what I'd like to do is maybe take this opportunity to kind of have a few slides that can walk through, give you a sense of the conditions we find ourselves in with demand for power in the world, kind of where fusion fits there, what are the advantages of fusion, a little bit of the story of our company and our approach, and kind of where we are in the commercialization. We talk a little bit about the site that we've announced and the deal with Google at the end. So with no further ado, let me see if I can actually successfully share this. That looks like that worked. So as Adam mentioned, I'm the Chief Commercial Officer at Commonwealth Fusion Systems. I've been here about 2.5 years. CFS started by spinning out of MIT in 2018 with a very different approach to fusion, which is let's use the existing best understood approach to fusion, which is this magnetic donut we call a tokamak, and then apply this key innovation, which is much, much stronger magnets that allow us to build a much smaller device, more compact device. That's something you could actually go build and finance. I'll talk about some of the milestones along the way to achieving it. But what is the context we find ourselves in? Like, it's basically there's an enormous surge in demand for electricity, and across various agencies who all are in the job of projecting what is the forward demand for energy and electricity. What you can see here is like there's a lot of difference in what the final projections would be out in 2050. But at the baseline, it's at least a doubling, and in some cases, like a multiply by 5 times the amount of energy that we're using and largely electricity. And the difference between the low end and the high end is, can we actually build a power source that can be clean, that can be firm, and that can scale to meet this demand? If we can do that, to build power and do it in a sustainable way, we're going to be on the upper reaches of that. And that's a good thing, because it means we've got abundant energy for many, many uses, for many customers, residential, commercial, industrial, but enabling us to do things that was not foreseen without this amount of build out. So you really can't unlock this next big growth unless you've got an innovative approach that can meet all the constraints for scaling. And we like to say that the universe decided a long, long time ago that fusion is the most energy dense form of power. What you look up when you look up in the night sky, many people say you see stars. We say you see fusion power plants. That's what those are. Every star is a fusion power plant. making an enormous amount of energy and doing that for billions and billions of years. It's actually kind of fascinating that we only theorized what's happening in the stars with Sir Arthur Eddington about 100 years ago. It's kind of a short blip in human history where we've actually even understood what's happening in the stars. But now we know that we've done experiments that show that we can make this reaction happen on Earth. But we haven't yet done it in a way that's obviously a commercial fusion power plant. But this is the most energy dense form of power. It's by combining two small elements together. And we'll talk about it here in this little picture. Two nuclei of hydrogen. You combine those together under the right conditions, and what you get is you get an enormous amount of energy released, and not much. The emissions are helium, a nuclei, and a neutron that come out of it. This is about 4 to 10 million times more energy dense than burning something, in terms of the energy out per mass. It's about four times what fission would be as well. So it is very, very dense. But why are we all talking about fusion? Basically because it has all these attributes that you'd want in any power source that could scale. So it is clean. There are no greenhouse gas emissions from producing fusion energy. It's safe. So when compared to fission, this is not a chain reaction. This is not, fission plants. By the way, I'm a fission fan. My first job as a nuclear submarine officer. So I used to drive fission plants underwater. But I love fusion for all these characteristics, and one of them is a safe bit here. It's not a chain reaction. It's impossible to have a meltdown. You need to achieve these conditions, and if you don't achieve these conditions for fusion to happen, and we'll talk about those conditions, but basically hot enough, dense enough, contained enough. If you don't achieve those, it just stops. There's nothing that happens after that, and it doesn't produce high-level radioactive waste that you have to worry about how you're going to deal with it, or that can proliferate into weapons. It's also a source of power that can be on demand. Press a button, it turns off. Press a button, it turns off. It's there when you need it, not when the resource is available, like solar or wind. It's also ultimately scalable because you're just basically building a machine that, in essence, makes energy from very, very small bits of fuel. It becomes something that it's affordable, it's modular, you can deploy it anywhere. And then finally, it's a secure form of power. So in the current world we live in, many, many countries are very focused appropriately on energy security for themselves. And that's national security, but it's also economic security. And the great thing about a fusion power plant is it's not really tied to any geopolitically fraught supply chain. With respect to the fuel itself, we use versions of hydrogen called deuterium and tritium. We will make our own tritium. We'll seed our plants with a little bit, but then we'll make our own. But deuterium is basically filtered seawater. And so if you have access to water, you have access to fuel. And it's nearly limitless fuel. So fusion can kind of break the paradigm of energy has traditionally been something where you dig something up and you burn it, or you put something on the ground that can take advantage of an intermittent resource, to something that you basically can build a machine that uses fuel that's available everywhere and own your own energy, and it can't be taken away. So it has all these great attributes, and it, again, back to the power density, it's really a reaction that can take grams and turn them into gigawatts. And this is why, by the way, fusion, if you look forward to any sci-fi book or series or movie, like what do they all have in common between humans and energy? Humans have mastered fusion. It's because of all of these characteristics. It's the kind of the holy grail. On the safety bit, it's just worth diving in a little bit further here. Like this is one of the main differences with respect to fission. And I'm a fission fan, but fusion's only produced under these very specific conditions. So again, it's a self-limiting process. If you don't have those conditions, it just stops. Like the worst day in a fusion plant, airliner crashes into a plant, it just disperses, like it just sits there. Nothing bad happens. So there's no significant health or safety or national security issues. We don't have the requirements that fission plants have for siting, and it's basically a clean, safe, sustainable source that you can actually, because it's so safe, you can put it really close to infrastructure. You can put it close to communities. The plant we're building outside of Boston, our nearest residential neighbor is like 400 yards away, and that's okay. So the world is really entering this race to make fusion power plants because of all those characteristics. And there are a bunch of companies that are doing this. The Fusion Industry Association just published their 5th report earlier this week that notes that just under 10 billion, like 9.7 billion has been invested. There's over 50 fusion companies pursuing commercial fusion. And there's also a whole bunch of efforts happening in China. So the same day that they announced the report being released, the Fusion Industry Association, there was also an announcement about yet another Chinese company funded to a very significant level, because China's pursuing this now too. Um, our approach is we're going to build this power plant. It's going to be a very modular power plant. It'll be about 400 megawatts of net electric power. It'll have a high capacity factor. There's no reason this plant can't run like most of the time, like other baseload power sources, like whether it's coal or gas or even fission. It'll be able to follow the load. We can ramp it up. We can ramp it down. There's no issues. You can run it like at 0. You can ramp it up to 100. That's all fine. It actually produces very high temperature and high quality heat, like 600-degree heat. So you can use it for other combined heating applications or industrial heat applications as well. And it's, again, flexible in terms of where you would site it. There's not the kind of onerous rules on where you'd site such a thing. So you can actually put it close to loads. And it's a relatively small footprint. It's a size, it would look to the grid like a gas plant in terms of like what its ability to provide power, to ramp up, ramp down, all those things. And it actually looks like a gas plant with respect to footprint as well. So like, I don't know, roughly 25 acres of footprint for a 400 megawatt plant, which is pretty dense and available to put in many, many different places. And so you can also swap it into existing infrastructure. If you're retiring a fossil plant, you still have an interconnect and a substation. Guess what? You can just plug one of these in, just build it there, connect it. And the reason there's this race going on, this may be somewhat obvious, but it's worth saying, like the market for power is enormous. It's one of the biggest markets in the world. Energy, electricity is what undergirds all of modern society. When you think about, obviously, all the productivity, transportation, communication, everything kind of relies on energy. So this is a literally $1 trillion market. And by the way, that's either for the capex of building out the power generation, or it's the sale of electricity. Either one of those, they're like $1 trillion markets. So we're going after that, and our intention is to build thousands of these power plants as soon as possible, certainly through 2050. People will ask, well, can fusion really scale? Like, how do we know that this can scale? And the short answer is fusion is a very, very efficient way of creating energy out of materials. So what we did the study, like what would it take to actually be able to build like 1,000 fusion power plants a year? And like, by the way, not many people build 1,000 plants a year, but let's just run this thought experiment. What it would take is about 5 First Solar factories. Those are factories that make thin film solar. One of the key components of our device is this high temperature superconducting tape. I'll talk a little bit about it, but it's basically a thin film deposition process to make this. If you have 5 of those factories, you're making enough of that tape, high temperature superconductor, to funnel to 1,000 power plants. And we'd also need like 1 Tesla factory to make the magnets that we make out of that tape. That's enough to also support and supply 1,000 power plants a year. And we'd have like 1 heavy shipyard that makes the big forgings and the big metal stuff that kind of goes into the plant. Again, those 3 things would be enough to supply 1,000 power plants a year. So this is pretty scalable. One question that comes up as well is like, why now? Like, what are we doing? Why is fusion so important now? Why are people talking about it? Well, the short answer is people have always said that fusion's very far away. It hasn't really been making technical progress. And the short answer here is that actually fusion has been making faster progress on its key objective criteria, faster than Moore's law. And people may be familiar with Moore's law, where you have a doubling amount of transistors on a chip every 18 to 24 months. And that's been going on for a long time, which has resulted in the amazing things that we use today that have powered our world and given us intelligence and communications and so forth. Well, fusion has been moving even faster than that. One of the problems is that our objective function, we were pretty far away from the critical milestone of more energy out than in. So I'll reference you to this plot that shows up here, which is basically a way of showing those 3 criteria that you need for fusion. So you do need it to be hot enough. This gets the material from a gas to a plasma, and then a plasma that's running hot enough that these particles will actually hit each other. And when I say hot enough, it's like really hot, like over 100 million degrees. That's what the x-axis is. Like it's in the form of electron volts, but it basically means temperature. And then the y-axis shows the other 2 conditions combined together. One is fuel density, so you have enough of the fuel around. The other one is confinement or confinement time. So if it's hot enough, dense enough, and contained enough, you achieve these conditions. And as you move up those curves on those confinement time and temperature, you get up and to the right on this chart. We have a bunch of lines, they're curved lines, that show places where you get to points where you have more energy out than in. That's the bright line, Q greater than 1. And what I'd say is our architecture, or this magnetic donut that we use called the tokamak, is the green ones. So the green ones have been making this great progress up towards more energy out than in. They hadn't yet gotten over the hump, and that was because magnets were only so strong, so you had to build it really big. That's the big construction project in France that's happening right now. But with our innovation of much stronger magnets, we can build something that's compact that can get you over that curve. That's what Spark is. We'll talk a little bit more about Spark. That's the plant that we're building right now outside Boston. That has a design point of a gain of over 10. So we're in the midst of building that right now. But the whole point here is that the progress on fusion has actually been very, very fast. And people who think it's so far away have not really been paying attention to how far this progress has gone and what the new innovations are that allow us to kind of hop the curve, so to speak. Um, and so what is Spark? This is an overhead picture of Spark. This is a demonstration device we're building outside Boston in a town called Devens, about an hour west. It'll be the fusion power plant demonstration device. This will show much more energy out than in on a large industrial scale. This plant will be producing about 100 megawatts of thermal power, and we'll be able to do it at the press of a button. Then we'll have to stop the machine because it's a lot of power. We'll have to get the heat out, and then we'll be able to do it again. So this will be able to be done repeatedly without like busting the plant. It's based on really well understood physics. We are operating in a plasma physics regime that's pretty well understood in a relatively conservative way. It's just we have a more compact device that's doing it. We actually work very closely with other partners, academic partners, universities, national labs. We kind of publish what our design is. We invite people in to look at our results. We do them in a peer-reviewed way. We've already demonstrated the key magnets here. I've done those in peer-reviewed ways. Some of the papers that we've written about our design are some of those referenced papers in plasma physics. So we do this in a very collaborative way. So it's like, I liken it to doing the work on your homework. Like you do your homework and you have a good result, great. But if you haven't shown your work, then people still question how'd you get there. We're showing our work. We're doing that with other people. But this is based on very established plasma physics. It's a machine that we're just building. So we're facing all the challenges in building a first complex machine, but we're already 65% of the way done building this. The key milestone for this one is showing net energy gain. We'll talk about our milestones and timelines, but that's going to come in 2027. So it's progressing rapidly. This is the inside of that main building we call it Tokamak Hall, where the tokamak will sit. We got some picture. That's a picture of what Spark will look like on the back wall. But we've got some rigs in there upon which we're going to hang our magnets, and then we pull it together. The picture in the upper left here is the thing we call our vacuum vessel. It's a metal thing that basically will hold the vacuum inside which the plasma will be running around. That's going to be also put inside those magnets. So this will be the first kind of greenfield development of a net energy gain diffusion device. So there's only been one other time in human history so far that we've achieved net energy gain. That's with the Lawrence Livermore experiment at the National Ignition Facility out in California, just a little bit ways from where I am right now. That was in December 22, a moment marked in human history, first time ever. Got more energy out than in, but that was a laser inertial approach. So a bunch of the biggest lasers in the world pounding very hard on a very small and exquisitely built piece of fuel pellet. And they've now repeated that several times. But this will be an approach that actually is able to do it pretty repeatedly without much fuss on waiting to do the next shot. It's also based off of pulling together a global supply chain for all the stuff that goes into this. We have a supply chain that's about over 1,000 global vendors from over 30 different countries. So that's all coming together with some pieces and parts that are showing up. The first part for the tokamak is actually in the very middle here. We call our cryostat base. That's a piece of equipment that we just installed and talked about it a couple months ago. So we're starting to put all the systems together, start commissioning them. And the end result here for Spark will be a industrial scale plant that produces about 100 megawatts of thermal power and with a net energy gain of well over 1. And just to reference, 100 megawatts of thermal power is like 500 to 1,000 times what the National Ignition Facility did. Like this is a significant amount of power. So as I mentioned, we work very closely with outside groups to make sure they understand our pathway. They can help to validate it as well. We'll invite them in to look at our results. Those will be all peer reviewed, but it's really been based on a bunch of research that's been done. There's been a whole bunch of research in fusion that's been incredibly helpful. We spun out of MIT, who had been doing some of the best research on fusion. MIT had its own fusion power plant. This is where our co-founders came from, and all the work that was happening there. But it's this is something that'll be validated by outside parties, and we like it because they actually will ask us the hard questions. They'll push us, and then it can be a mechanism by which we can bring the best in the industry, the smartest people into what we're doing, even if they're not employees of CFS. So it's been an important part of our company from the very beginning, building out the fusion ecosystem, because a company can go build a demonstration device, but that is necessarily not sufficient. We're building a company to build a machine, to build an ecosystem, to build an industry that hasn't existed before. And so there's a lot of pieces and parts that need to come together for that. I'll talk a little bit about the regulatory pathway here too, and licensing. But what makes this all work is this material. What makes it work now is this material that I talked about, this high temperature superconducting material. So on the left, you see a picture of it on a roll. It looks kind of like an old cassette tape. Like that's the kind of tape that we use. But this tape is actually mostly steel with a little bit of copper on either end. And there's a magic layer inside, a couple microns thick, of this high temperature superconductor, which won the Nobel Prize back in 1986 and was only available in like commercial quantities in an industrial way probably in the early 2000s. Then we have really scaled up this industry. But the big deal is that the current best, before using this high temperature superconducting, the best like device, fusion device, the only one that was being built that would show net energy gain is the picture on the far right. This is a project called ITER. It's in the south of France. It used the best magnets at the time, but those magnets are low temperature superconductors because high temperature superconductors had not been available. And it shows up in this middle plot. The low temperature superconductors are this orange curve. That's the design space you have. And the high temperature superconductors are the gray design space. So it opens up the design space. The biggest deal is that, yes, they both superconduct. Yes, high temperature is higher than low temperature superconductors, but it's still like 10 to 70 degrees Kelvin, so it's still really cold. But the biggest deal is low temperature superconductors will no longer superconduct under very strong magnetic fields. So you're capped on how strong a magnetic field you can hold, and therefore you're capped on how much you can contain that plasma, these charged particles that are running around. And with high temperature superconductors, you're essentially not really capped. There is a cap, but it's pretty far out. You can have a much, much stronger magnetic field and still have superconducting. So you're able to run a lot more current through it and then keep it going until you have a much stronger magnetic field, which really allows you to tighten down and hold that plasma really tight. That leads to the picture that's next to the one on the right. That is our Spark machine compared to ITER. It is going to be much more compact and still have the same plasma physics and same performance. Part of what we're doing to go build that machine is we're actually building the magnets ourselves. We have vertically integrated on this. This is one of our secret sauce where we know how to build these magnets, which are more than just wrapping this superconductor around in a circle and getting a big electromagnet. There's structures around it. How do you think about it? How do you protect it? All those things. So we went from building our manufacturing capacity where we build out like one of these little pancakes. Like in the first time we're doing this, it probably took us like 6 months, and then we're down to like a month per pancake. Now we're spitting out a pancake per day, where I've already built much of the pancakes that would go into our magnets in Spark. And it's a very modular process. This is a production line that's now running 24/7, 3 different shifts. And it's modular even in just one device. So we'll have 18 of these big D-shaped magnets arranged in a donut. Each of those big magnets has 16 pancakes in it. So for those of you who do math quickly, that's 288 pancakes in one device. So we're already pretty much modularized and running through a manufacturing line. We're already dropping down the manufacturing curve on time it takes, cost to do these things. So this is something that no one else really has, this manufacturing capacity, and it's going to allow us to scale much more rapidly. And as a company, I'll just step back and say, we're really been thinking about how do we build a company that can deliver, again, not just a fusion power plant or a demonstration device and then a power plant, but how can we scale that? And how can we deliver it not just on the technical side, but all the other ways you need to think about it. So we do certainly have a bunch of the best plasma physicists in the world in our company or working with our company. But we're not really doing science discovery. We're taking the best of what's known and then putting it into a machine that we're just basically building. And as I mentioned, we've done a bunch of peer reviews so people can take a look at it. But we're the largest private fusion company by far. We've raised over 2 billion, roughly a third of all the capital raised by private fusion. We have over 1,000 employees working on this. The list on the right shows where some of these employees have come from. Some of the companies have done the biggest, hardest things that people said were not possible. Some employees come from places where they produced millions of units a year, automotive or other, or chips. And some of them come from, technology companies that have been really thinking about innovative ways to approach problems. And then, of course, from some of the best labs and universities in the world that have been focused on fusion and physics. But it's interesting, like one of the things that we did early on is we also realized, again, you can't just build a device and then hope the world takes it. So one of the things we recognized early is that like the licensing process for a fusion plant, like what is that? Oh, it doesn't exist. No one's ever built a fusion power plant. So we work with governments around the world to try and make sure we've got the right safety approach focus on licensing these power plants. And in the world today, there's 2 countries that have already decided a different path to license fusion power plants, different than fission, which is the normal, like people say, oh, we'll just regulate it like other nuclear plants. And like, well, we actually avoid calling this a nuclear plant because it has connotations to it. It's actually a fusion machine. But the UK and the US have already decided they're going to regulate it more like particle accelerators because that's effectively what it's doing. It's accelerating particles around and then having them fuse and make energy. And that allows us to much more rapidly license a fusion power plant and with much less onerous terms. And it's all safety appropriate. It's because we don't have those safety issues. And this results in something that would take us, I don't know, probably like 18 months and less than 10 million to actually get a license for a fusion power plant versus for a fission plant, that'd be probably like 5 to 10 years and 500 million to a billion. That's just to get the approval to go build that plant. It's not the cost of the plant itself. So that will enable us to deploy much more rapidly. But also we have because we're just managed on how we handle materials on site, we'll be able to even improve existing plants without having to re-go through that process, which is something that fission can't do. But this is one example, the licensing, but we've been working with governments and labs and universities to make sure that we're all set to deploy rapidly when we get there. So what are our timelines? What's the timeline to deliver fusion power? Well, starting on the far left, our founders worked on kind of a record-setting fusion plant at MIT. It's called Alpha-Tor CMOD, is what that picture is. And then when they realized we can use this material, a superconductor, to make much, much stronger magnets, that's when the company was formed, spun out of MIT in 2018. Our Series A funding was all predicated on, can you go build that magnet, like a really strong, large magnet, where people would say, you can't do that. There's not even enough material in the world to do that. No one's ever built a magnet like that, not with that architecture. No one's ever built, they built very strong magnets, but much, much smaller scale. That's what our Series A was to do. We did that after 3 years, and we showed this very strong magnet. That then led to raising a Series B of 1.8 billion because people said, I see that magnet. I see how you could put those in basically in a circle, make a donut, and you would have a fusion machine that hits net energy gain. So that's what our 1.8 billion was meant to do. Go build that device, Spark. That's the one we're building. I just showed you outside Boston, over halfway done building it. Our timeline for that is to complete building that, commission those systems, and then show net energy gain in 2027. Our next step from that is then to go build our power plant. We call our power plant ARC. That's the 400 megawatt power plant. We're already in parallel getting ready for that. What we announced back in December was the site for that. I'll talk through a little bit more. But when you talk about going from Spark to ARC, Spark really paves the path for ARC. It demonstrates most of the systems that would appear in ARC, the power plant. We say like 13 of the 17 systems are actually demonstrated by Spark. The things that aren't demonstrated are like the conversion of that power to a molten salt and then transferring that to a steam cycle. So we're not demonstrating that because, well, we've turned hot things into steam and spun a turbine for a long time. That's not really a big de-risking for us. But we are also pursuing things like showing you get tritium production underway. Something that we're going to be doing on the sideline, showing we can operate this thermal salt, this molten salt. So we'll be doing those as well. But But Spark basically proves out all the fundamental characteristics of Arc. It allows us to shrink the design space for Arc, and we're in the process of designing that right now. But this will become like the de facto commercial, version of Fusion, and so we're super excited about it. When I said that on the commercial side for Arc, we've actually even already hit some milestones. So we did announce the site. This is the kind of rendering of the Arc design. We've already done some initial designs, but we announced the site in Virginia back in December. And so this will be the site of the first fusion power plant. We announced that site in a press conference with Governor Youngkin and with participation from Dominion Energy. So we've been keeping utilities really informed of our progress so they kind of know where fusion is. And in the process of doing that, Dominion Energy's CEO came up and visited us. And when he saw what we were doing in Devens with Spark, he said, "Oh my gosh, we should do something with CFS, like not on the third plant, but on the first plant. We should try to get it in Virginia." 1 year later, we have a joint development agreement with Dominion, and we're siting our first power plant on a Dominion-owned property, which shows up here, which is very close to their large already existing generating station in Chesterfield County, just south of Richmond, Virginia. And the site is great for many reasons. Transportation access it's like a mile off I-95. You can see that there's a water pathway there. It has rail access, so it's a great physical connection. It's got a great workforce. In this region with Dominion Energy has a workforce there. It's close to nuclear Navy stuff. So it's a great workforce. It happens to be the site of enormous customer demand. Virginia is the base of many, many data centers, and there's a huge growing demand, not just for clean power, but clean firm power. So you can bring capacity on, but also in large chunks to fuel the data centers, as well as large industrial customers there as well. We had significant state support in citing this in Virginia. Virginia's been great in terms of support. We actually have great local support as well. We met with the local community, educate them on what is fusion, what are we going to, what is it, what is it not, making sure we're building up the support there. We've had encouraging meetings so far. We continue to have those. We just did a public meeting like a week ago as part of our process. We have already submitted a conditional use permit to build a fusion power plant. First time that's ever been done in the world. We're doing that in Virginia. We're in the process of doing that right now. We're going to be going in front of the commission in a month or two. So super excited about the support here and the location and our partners. The other thing that we just recently announced, and this is like the last slide, and then we can take questions, is the largest fusion deal in history, which is we signed a deal with Google who will take half the power from this plant. So 200 megawatts of the 400 megawatt plant. This is a huge validation of the approach that we're taking and a huge validation and commitment from customers. It really shows there is a huge demand for fusion, but it was more than just an offtake agreement. This was more of a strategic partnership because Google came in with a significant investment. As I mentioned, they've already been invested since 2021, but this is an additional investment. And they really looked at this and said, this is a game changer for their business, but it's also a game changer for the world. And Google has a history of investing and supporting technologies that can help themselves, but also help the world and the communities in which they operate. I know this, I was previously at Google several years ago, and know that the teams are really focused on what can they do to help enable their business, but help to enable better access to clean, firm power for the world. We see a quote here from the CEO. Really think this can be a transformative technology. But part of the agreement is also not just the offtake and the investment, but also an option for Google to get power from future Arc power plants. So it's not even this agreement itself. It's not even just for the first one. It's actually setting the roadmap, the path for multiple power plants, and that's another really, really exciting part of this. So I ran through that pretty quickly. I'm happy to take questions, but at the end of the day, fusion has held great promise. It's always been the holy grail of energy. We are getting closer and closer to deployment. And one of the educational challenges that we face is that fusion is coming sooner than many people think. And the people who come up and visit us and partner with us really understand, they get into the meat of it and they understand this is actually happening. This is coming. And they see Spark, which is the plant we're building outside Boston, and they say, this is real. And so it's coming sooner than you think. We're extremely excited about our progress, about the ability to deliver, and the partnerships we had to go do that. So with that, I'll end and take any questions.
Thank you. And for those just joining us, our guest today is Rick Needham. He's the Chief Commercial Officer of Commonwealth Fusion. This program is on the record. It is being recorded, and the video will be on our YouTube channel. We have a big turnout today, and I've seen a number of people from MIT, USC, other universities, and we will get to your questions. We want to get to as many as possible. Please put them in chat, address them to our producer, Judy Kang. For our first question, let's go to Llewellyn King, founder of Energy Daily, syndicated columnist, host of White House Chronicle, where I'm also a co-host. We've done 2.5 hours on fusion energy research. Llewellyn has written about and has visited Commonwealth Fusion. Today he has the first question. Llewellyn, over to you.
Yeah, thank you, Adam. Great. If your machine is as successful as you hope it will be, and as you plan that it will be, what is this going to do to the competition just getting going from small modular reactors? Are you going to be a big disturbance in the marketplace?
It's a great question, Llewellyn. There's a huge demand for clean, firm power in the market today, and it's not. By the way, it's not just everyone. What's in the headlines is AI and data centers. Yes, there's growing demand there. The demand for data centers has doubled over the last 5 years. Is anticipated to double the next 5 years again, and quadruple in the next 10 years. So yeah, big growth there. But that's actually just a piece of the global demand for power. There's also appliances and cooling and buildings and infrastructure and large manufacturing onshoring in many countries. So all that's to set the context that there is an enormous amount of demand for clean, firm power. So the short answer is the market is so massive, like $1 trillion market. There will be ample opportunity for anyone who's able to deliver clean, firm power, but importantly, deliver it like actually deliver it, show up on time, on some time scale that you can then scale and grow and deploy more widely. So I would say, with respect to other approaches here, and like people talking about solar plus batteries, or wind plus batteries, or geothermal, SMRs and advanced fission is certainly one of the ones in this category. I think they will be in some sense challenged by the regulatory and licensing pathways for those technologies, and there's appropriate mechanisms why those licensing pathways exist, because it is a chain reaction that you effectively control to slow it down to make sure you're getting energy out of it. When I started, as I said, I'm a fission fan, so I really hope that some of those advanced reactor concepts actually get deployed, actually show their progress, and do it hopefully at a cost that makes sense, because some of the cost numbers are relatively high. But deploying a first one, yes, it's going to be admittedly higher than the final one. But at the end of the day, I just think the market opportunity is so massive that it can take many, many solutions. I just honestly, I believe that fusion, when it gets to its first commercial plants and it starts coming down the scale curve, it has some inherent advantages in the reaction itself, and therefore the safety profile and the licensing of it, that it will be able to be deployed much more quickly and much more widely. That doesn't mean to say that if a country wants to deploy fission, they can. Ultimately, the arbiter of what is the successful power source will be economics, right? It'll be who can come down the cost curve and who can deploy energy in an affordable and scalable way. And we're encouraged. We think fusion will be ultimately the cheapest form of clean firm power known. Again, that's why it shows up in all the sci-fi things. But there's work to do. It's not like it's a given. We'll have to do work to do that. But I think at the end of the day, there's room for other approaches, and we encourage all of them to be as quick to get to on the cost curve as possible, because you can only drive down the cost curve once you're on it.
So you don't think we're going to see a situation analogous with VHS and Sony in tape, in the development of broadcast tape, where two competing attractive technologies came to market simultaneously, and one eclipsed the other? If you're sitting in the C-suite of an electric utility, would you not be worried about stranded investment if you invested billions of dollars in small modular reactors, when you could maybe get a better result with the same billions of dollars in a fusion machine?
Yeah, I mean, I would be worried about stranded costs. The one difference between like the Betamax and VHS is we're not building a specific plug that you need for fusion power. Like everyone has the same plug, 120 volt, 240 volt, whatever it is. What you want is you want electricity. And so both things provide this thing. But it is a reasonable question to ask about stranded assets. By the way, some utilities are now including it in their IRPs, like build out of massive amounts of gas. That's a real question. Like, are you going to build out gas plants that have lives of 40, 50 years? If you can see a pathway to something in 10, 20 years that's actually commercially better and can supplant those other forms of firm power. So that's a bit of a conundrum that utilities will face now. What we would say is utilities should make sure they're considering all the pieces of those wedges when they start doing their integrated resource plans. And traditionally, they haven't had to think about fusion because it just hasn't been in the realm of likely deployment in their timelines of their IRPs. It is today. It is today. And that's why those C-suites should be thinking pretty carefully about where they're placing their bets. But many of them are doing in all the above kind of bet. Like Dominion Energy is a great example. Like they have to look at all solutions in order to meet the demands that they're seeing. And we're very encouraged that they're now considering fusion as one of those. But they're also looking at fission as well.
We're getting a lot of questions now from participants. We have the first one into chat was from Matthew Wallen, noting the world's race to get commercial fusion power plants and particularly competition with China. What's necessary to make sure that the United States gets there first and leads the revolution in fusion energy? How do we make sure the world turns to America for this technology and the commercial benefits that it will bring?
Yeah, it's a great question. It's one we get frequently, actually. And our CEO is just down at an event in DC. So there is this real race going on. And when we're asked typically who's our main competitor, the answer tends to be China is the main competitor. And China is actually putting quite a bit of investment into fusion today. Funding at a level that's probably twice the amount that the US is putting into fusion, focused more on commercial now, commercial elements of fusion, not just the science and research bit of it. They're graduating 10 times the number of PhDs. They just announced this week another $2 billion funding level for a company. It's hard to understand exactly. Okay, most of that supports like state support and state entities that are investing in. So it's really government money going in. But if you step back and you think about the history of technology deployments, especially in energy, and where the innovations have come from, but where the scale and the manufacturing benefits have gone to, it's not a good story for the US. Like we have seeded the invention of some of the critical technologies of today, seeded with an S, like solar, like developed here in the US, but then seeded with a C, the manufacturing, the scale up to countries like China, right? We've done the same thing with batteries, lithium-ion battery, invented here in the US, now being made at scale in China. You think about wind, we still have a few companies, GE still making wind turbines, Vestas in Europe, but many of them are now in China. So there's a history of innovation, but lack of converting that into a scale building business, manufacturing business where we kind of own that technology. The good news about fusion is that list of who are the top 10 companies deploying commercial fusion, like it's still empty. It's still a bunch of question marks. So we're early right now. We have the opportunity to not repeat history and not make the same mistake, but instead actually support it at a level that would ensure that we not just maintain the edge on innovation, but maintain the edge on deployment and commercial reality, and in essence, then reap all the benefits of a growing industry that makes stuff that sells it to other countries around the world. And so we have this ongoing conversation with the administration on what does that mean. Right now, we're the largest participants in a program established by the DOE called the DOE Milestone Program. It's a program that was modeled off of what was done with SpaceX. And the simple idea is a company, if you achieve a critical technical milestone or demonstration milestone, government will give you money that's cost shared. But it's only pay for performance in essence from the government. And so DOE has set up a program just like that for fusion. And we are the largest recipients of that, but it's not funded at a level right now that would meaningfully change the trajectory of commercial fusion. That is a vessel by which, if you put enough funding into it, you could dramatically change the prospects and allow private companies raising private capital. We've raised $2 billion of capital ourselves to compete with government funded entities over in China. Like I was literally just asked on a Reuters call this morning, is it unfair that private fusion companies have to compete with a government? And the answer was yes, it's unfair. Um, but we have a history in the US of punching through with, like, you would think these are large numbers. They're kind of small numbers for government, with like a $10 billion, who knows what the right number is it 10 billion, but you could punch through technologies that didn't exist that become suddenly part of your tool chest. Internet from space, punch through. mRNA vaccines, punch through. Like, the space race, punch through. Like, these are things that if you invest the right amount of capital at the right time, you become the beneficiary of a tool that did not exist in your tool chest. Fusion is at that point right now. It's at that commercialization point. And so if there was ever a time to really double down and support the commercial deployment of Fusion, we think now is the time to do that. And you don't want to lose the race because you're, twiddling your thumbs and wondering how best to do it. I'll tell you what, China's not twiddling their thumbs. The US put together, the experts in Fusion were asked to put together, what's the roadmap? What's the plan of all the facilities that you would build, test facilities for materials, for neutron source, all that stuff. But we never actually got it built because we kept questioning, should we do this, should we not? China said, thank you for that plan. We're building it. And now they're building things that you can see from space. And they're not PowerPoint pictures. They're buildings. We need to get off our collective seats and go do what we say we wanted to go do, build a future. But we can do that best with some government support.
Related question, what are your biggest challenges for the next 2 to 4 years?
Yeah, so 2 to 4 years, that puts us at, call it 2029 on the outside. So the biggest, a challenge right now is just go get that spark plant done. We're building a pretty complex machine. We're on the path. I think we're fine. We're hitting our dates and so forth. But it is a complex machine. It'll be the first machine ever that's going to have a continuous ability to do net energy gain shots, and so that's fine. I think some of our other challenges will be continue to build up the supply chain for the critical pieces that we need. We already have a global supply base of about 1,000 vendors. We have pieces and parts that are now showing up to Devon's, our site outside Boston, to go put and integrate those things into Spark. I think we'll need to continue to work on what are the kinds of materials that we can actually best use, the optimal materials inside a fusion power plant. We haven't had to think about this in the past, but materials that can withstand, a neutron flux, that can still perform in the environment in a fusion plant. So there's work to be done there. We have probably the largest and most advanced materials team in the industry focused on this, but we're actually partnering with other folks, and some of this is through government funding, to develop programs that can better, in some cases, use AI to better figure out what are the materials that we'd really want to focus on, to then really go dive deep and spend some time assessing those materials. There's technical stuff related to how do we exhaust the heat from a fusion plant, how do we do the tritium breeding, those things. And there are programs that the government's funding, not just the US government, but in some cases the UK government on the tritium side, and thinking about how to do that. But I think one of the challenges that we also face is there's always going to be the technical challenges, are kind of the more ecosystem related challenges. Like, good news is we have a regulatory pathway in the US that's pretty clear, and we know what that looks like, and we know what it takes to get a license. And why do we know this to be true? We already did it in Boston. We already have a license to operate a fusion plant in outside Boston, and fits in a manila folder. So that's a place where the government has stepped up and said, we'll take a hard look at this. We'll dig in. We'll know it. We'll understand it, and then we'll make the appropriate policy decision. So that's already happened. But it's also going to be like, who are the partners that can help you deploy this at scale? So it's always easy. It's easy to be the person that says, well, I'll just wait until the third plant's ready, and then I'll go, then I'll pick up the phone and call them. Like, well, if you wait that long, you're going to be in the caboose, and you're not going to be the top partner of ours. So because there are so many other companies that are actually willing to take a hard look, to dive in deep, to understand the details, and say, this is happening. Google is an example of this, of signing that offtake agreement, and also then investing in the company, and then even having a mechanism for options for future power plants. So part of it is the challenge is actually continue to build up those partnerships. Because one of the things that's not going to be easy is, how do you finance the very first fusion power plant? Well, that's hard, but we try to make sure people understand this could be a whole new industry that could become by itself the biggest industry in the world. So if you're a very if you're very focused on what's the monetary advantage that my company can get, well, this is a whole new industry that can expand what you do, whether it's like the insurance industry, or it's the construction industry, or it's the manufacturing industry, be doing large forgings. Like, this is a whole new industry that hadn't existed that could become the biggest industry in the world. So making sure the wider community understands that and is willing to step in, to lean in, because it's easy to wait for something and harder to be the, on the cutting edge. But if you're on the cutting edge, good news is you'll benefit, you'll get the benefits first too.
Related to what you were just saying, your investors include Bill Gates, Singapore Wealth Fund, and others. But a question in chat: how do I invest in your company?
It's also a question we get frequently. So we're still a private company. We've still been raising private capital. There is no easy mechanism by which a private investor can invest in CFS, or frankly in Fusion generally. At some point, in the future, I'm sure if we eventually become a public company, that's a separate conversation in the future. So I suppose one of the ways, yeah, so we wish there was an easy answer here, which is you can invest, but there's not an easy way to do it now. But in the future, there should be some interesting options to do that. Well, maybe I'll just leave it there.
And just one more question from chat before we go to somebody else who's just joined us, which is you've talked about megawatts, you've talked about selling power to Google. How close are you to selling power to homes?
Yeah, great question. We've talked, we even talked about this within the company. The short answer is it might even be possible with diverse power plants. Just depends on who the off-takers actually are. And also, by working with Dominion directly on the development of this project, one of the reasons they want to do that is to really understand fusion power, to understand how these plants get built, to understand their operations, such that in the future they could be the buyers, the procurers of fusion power plants for their entire footprint of customers, so residential homes as well as commercial, industrial. It just so happens that the hyperscalers are very uniquely positioned to be excellent, like beachhead customers for this power, the power coming from a fusion power plant. And why is this? It's because they're able to think further out in time because they have large infrastructure needs, large energy needs, and they're in planning cycles that now go out many, many years. And so they can actually think about a technology that's in the future and sign up for some of that. They also have the ability and the willingness to pay more for some of these first power plants because it is, in essence, the foundation of what they do. It is the foundation of their business. Electricity is what drives these businesses, and it was what drives their growth. And we've all seen the news, right? The hyperscalers are investing like $300 billion just this year in building out data centers. That does not include the energy infrastructure that's needed to then go power those sources of intelligence. And so there's a huge, huge growing need for power. But they're also, I would call them like technology optimists. Throughout their history, they have understood new technology and been willing to invest early to bring that to fruition, right? These are companies that have invested in like self-driving cars and have done that for a long time. And now we have self-driving, like I live near San Francisco. These are driving around. They can see technologies that others may not view or be very skeptical about and be the ones that are the naysayers, but they tend not to be the naysayers. I know this because I used to work at Google too. And I know the DNA in the company is to find solutions that help their business, but also then drive improvements for their communities. And so when you ask about when could power from a fusion power plant power a home, the power in essence will be going to the local grid. So within Virginia, the power will be going to the local grid. It'll be powering lots of things, but Google is the one who's going to be helping to make that happen by paying for that power. And Dominion is going to be helping to make that happen by partnering with us on developing that. But the power actually will go to the PJM grid. This is not power that's going directly to a data center, but they're the ones that can help enable this to happen. So in essence, the electrons, which are, they're fungible. Like we're going to be putting power into that local grid. Everyone's going to kind of benefit from that additional capacity being on the grid, but someone's going to be paying for it. It's not the residential customer who's going to be paying for that. It's the Googles of the world who are going to be paying for that first one. But eventually, utilities will want to be deploying these plants themselves, and the cost for those will be spread on the rate base. They'll figure out what's the right way to finance these things. But we see a future where if we're our intention is to deploy thousands of these plants. That's going to go to every customer, and not just in the US, globally. We had a bunch of global partners who have been knocking on our door vigorously. How can we deploy fusion power plants in my region, and willing to help partner on that. And that's great, and it's wonderful, and it's fantastic. We just know that the pathway to many starts with one, and so we really got to be focused on delivering this one in Virginia.
Quick question, just if you could just put a number on this. If your first power plant in Virginia, if all of that power went to homes, how many homes could it power?
So it'd be 400 megawatts of power at a high capacity factor. It's several hundred thousand. It's, I don't know, 200, 300,000 homes, I think is, I'd have to do the math. I'm doing the math in my head, but it's several hundred thousand homes. Yeah, for
So
sure.
that just gives us the order of magnitude of how big this is.
Yeah.
We're joined now, I see on screen, Ryan Bucas, who won the first MIT Build a Better World Service Award 2 years ago for leading, quote, efforts to organize the national fusion community and replace territorial competitive lobbying with a unified agenda to promote fusion through a compelling narrative about the role that fusion energy could play in meeting future climate goals. Ryan, this really helped move fusion research along, didn't it?
Yeah. Well, it's been. Have you got me here?
Yes.
We got you.
Okay. I just see a little corner here. Thank you for giving me a spot in this very important meeting, because Rick has just presented something which is completely compelling as to what and how Commonwealth Fusion is doing. I started now somewhat more than 15 years ago, coming from the environmental community, discovering that if we were going to do anything about climate, we had to have a new energy source. It had to be scalable, it had to be safe, it had to be, well, something that fusion seemed to be the only solution that looked like it was practical and that could be there. And that led me over to MIT, which happened to be my alma mater, and to talk to people over at MIT, and I'd had other earlier contacts there. And it was my privilege to be able to do things to help support the MIT program when it went through some difficult times with respect to funding, and things that continued on keeping the tokamak at MIT running, and the process at MIT, which led to really a student group developing the ARC design, which meant ARC, affordable, robust, and compact. And then discussions across Dennis White's table in his office to say, well, can't we make it smaller? Can't we make it cheaper? Can't we make it quicker? Or not the we, how the heck me? Why am I saying we? Can't it be done quicker? And that's led to Spark, which meant soonest possible, affordable, robust, and compact. And that's what then spun out Commonwealth Fusion from MIT. So meantime, of course, I'm not a physicist. I'm not going to be able to do the physics and so forth. I spend a lot of time walking around and talking about fusion and the importance of fusion, and the fact that this new energy source was not optional, not a neat to do, not a nice to do, not a fun way to get new papers published. It was essential to the world to have this new energy source and have it in a hurry. And that led me down in Washington, and my white hair. When I started, I had dark hair, but it became the point that people would see me in a photo line, or politicians would see me coming around, and one former president was heard to remark when he looked at the group, he said, uh-oh, the fusion guy is here. So that's led to now Don Beyer, interestingly enough, representative from Virginia, has created a fusion energy caucus in the House with more than 100 members of the House. And just getting people up to date and understanding the advantages of fusion energy is something which has been very important to me. And I should comment with respect to Adam's question. I need to emphasize that I don't work for any lab doing fusion. I don't work for any company doing fusion. I don't have any investment in any company doing fusion, directly or indirectly. And the result is that maybe I have some position as a person who says, I'm not in it for me. The MIT Alumni Association honored me hugely by giving me the first World Service Award. That was not an award for service to MIT. They said it was for service to the world. And that is where I had to say, and my final comment here is, I told them, and I said in my acceptance remarks, that I only received that award as a proxy for the people who had spent whole lifetimes before I had been involved in trying to bring fusion into fruition, to get the physics done, to get the thing, to get the new magnet material. You know, there's the stuff. Without that stuff, ARC doesn't exist. This industry won't exist. Right? And getting these things made, and all those people have made it possible for the presentation that Rick has done so ably. It's been a huge effort. I got an award, but that was only something that recognizes the huge amount of work that had been going on for decades before I became involved. So sometimes you get an award for talking a lot and not doing very much. Commonwealth Fusion has people who are doing, and so do other places have a lot that they have been doing, and in other countries. So all I can say is, Adam, thank you for giving me an opportunity to give a reflection on 15 years, 16 years now, having recognized through the Nature Conservancy that we had to do something different, and that mitigation and adaptation was not the solution. And Commonwealth Fusion is just so enormously exciting. And the other companies. At MIT 2 weeks ago, they had the first IEEE, that's the Electrical Engineers, Fusion Engineering Conference for 2025. That wasn't physicists. That was people engineering power plants. They had to close the registration at 700 people. And people were complaining they couldn't get to the meeting. They said, we can't accommodate more than 700 people. And that was the people who were going to be building the fusion power plants. And what's wonderful is that the average age was about 35 if you looked around. Isn't that great? That's people 50 years younger than I am. And so, Rick, would you light a fire under those people? What the heck is this 2027 nonsense? Okay? We need this now. Okay? Get going. Come on, guys. Hubba, hubba.
I'd say we're
That
yeah,
sounds
thanks,
like a
Ray.
final question to you.
Yeah, it's actually fascinating because Rain, I appreciate all your support. And like all the advantages of fusion, it's actually really fun to talk about fusion because it has all these great characteristics of a power source. And when I run through those, people tend to ask, so what's the downside? And it gets right to that last comment, which is it's not here today. I wish it was here today. My job would be really easy if it was here today. But we're working every day as hard as we can to pull that fusion future forward. That's the way we decided on our architecture. It's the way we decide on our approach. It's the way we decide on working with universities and labs to actually speed us up, not slow us down. It's the way we decide on partnerships. It's the way we decide to go to commercial. Everything is focused on how can we, as fast as possible, deliver fusion at scale. And we've been blessed with investors who believe in that and believe in us. We've been blessed with partnerships along the way. And I think it's a testament to our approach, to our ability to set and meet aggressive milestones, and the team that we built to go do it. And so trust me, we're going as fast as we can to make it happen. But we're doing it by bringing the world along with us. So it's not just us in some cloakroom saying, trust us, we did it. It's us out in the open saying, we did it. Look at our results. peer review them. It's done in tandem and in partnership with a whole bunch of people. So we get the best minds thinking about it, because that's the way that fusion will actually get deployed. Not just the first plant that you wonder, did it really work? But that's the way we deploy it at scale. So it's the one downside of fusion. Like I wish it was coming tomorrow. 2027 is pretty aggressive. It's so funny. People ask us on the other side, well, I don't think it's going to happen that soon. Well, we're working every day to make it happen. So we're super excited about everyone's interest here. Really appreciate the opportunity to talk about it. And the moment I get off the call, I'm going to be working hard to go get those commercial relationships to get us going.
Well, Rick Needham, Chief Commercial Officer, Commonwealth Fusion, I know you have to run. Thank you for joining us. We hope you can come back and talk about this some more as your progress continues. So
Happy to.
Thank you once again to all of you who joined us, and we look forward to your joining us again in the future. Our next public program, again, July 28th, next Monday, on the meeting of the BRICS countries in Brazil and possible expansion to Ethiopia, Egypt, and other African countries. Until then, thank you, and we are adjourned.